7 Earth-sized planets orbiting the nearby TRAPPIST-1 star about 40 light-years away.
NASA's latest mission has unveiled 17 exoplanets that defy our Earth-centric view of life. These are new worlds that challenge our very idea of habitability. With oceans possibly hidden beneath icy shells, these planets open up new possibilities for life beyond Earth. What secrets do these hidden oceans hold? How do they transform our search for extraterrestrial life? Join us as we explore the depths of space, where each discovery brings us closer to answering the age-old question, are we alone in the universe? The concept of habitable zones and ice-covered exoplanets. When we think of habitable exoplanets, we often envision worlds similar to Earth, situated in what's known as the habitable zone of their star systems. This zone, also known as the Goldilocks zone, is where conditions are just right for liquid water to exist, not too hot, not too cold. Traditionally, this concept was focused on the distance of a planet from its star, under the assumption that this was the key factor in maintaining the right temperature for liquid water and, by extension, life. However, recent discoveries have expanded this view. In December 2023, NASA's study of 17 exoplanets highlighted that even worlds outside the traditional habitable zone could harbor life, provided they have sufficient internal heating mechanisms. This internal heating can come from tidal forces exerted by their host stars or the decay of radioactive elements, keeping subsurface oceans of water liquid beneath icy shells. This concept isn't purely theoretical. We see examples of it within our own solar system, with moons like Jupiter's Europa and Saturn's Enceladus demonstrating subsurface oceans heated by tidal forces. These findings challenge our previous notions of where to look for life in the universe. No longer are we limited to searching for Earth-like planets in the habitable zone of sun-like stars. Instead, we're learning that life could potentially thrive in a much broader range of environments. Geysers as windows to alien oceans. Building on the intriguing possibilities of life beyond Earth, NASA's study brings to light an extraordinary aspect of these distant exoplanets: the prediction of geyser-like eruptions. Picture geysers on Earth, blasting water and steam into the air. Now imagine this on a grander cosmic scale. These potential extraterrestrial geysers could periodically burst through the ice crust of these exoplanets, offering a window into the hidden oceans beneath. This isn't just speculative science fiction. In December 2023, scientists at NASA predicted that all 17 of the identified exoplanets could exhibit such cryovolcanic eruptions, thanks to the internal heating they receive. This heating, stemming from radioactive decay and tidal forces, could maintain oceans beneath the icy surface, leading to the possibility of geyser activity. Why is this significant? These eruptions could provide crucial observable evidence of subsurface oceans and, potentially, life. Imagine observing an exoplanet, and suddenly, a plume of material erupts, hinting at dynamic geological processes and the existence of liquid water. Such an observation would not only be spectacular, but also groundbreaking in our quest to understand these distant worlds. It's a thrilling prospect, offering a glimpse into the subsurface secrets of these ice-covered exoplanets and opening new avenues in our search for extraterrestrial life. Internal heating, tidal forces, and radioactive decay. The concept of internal heating as a key player in maintaining liquid oceans under icy surfaces of distant exoplanets is both fascinating and pivotal. This heating, crucial for sustaining potential life, arises from two primary sources: tidal forces exerted by the host stars and the decay of radioactive elements within the planets themselves. Tidal forces, similar to those affecting Earth's oceans, result from the gravitational interaction between the exoplanet and its star. This interaction can generate significant internal friction, which in turn produces heat. Think of it like repeatedly bending a metal wire. The action creates heat through friction. In the realm of these exoplanets, this heat can be sufficient to keep subsurface oceans in a liquid state, despite cold surface temperatures. Adding to this is the decay of radioactive elements within the planet. Just as Earth's interior is warmed by the decay of elements like uranium and thorium, these exoplanets too could be heated from within. This radioactive decay acts as a long-lasting internal furnace, contributing to the warming of subsurface oceans. In a way, these exoplanets are similar to thermal flasks in space, keeping their oceans warm against the cold of the cosmos. This combination of tidal heating and radioactive decay presents a powerful mechanism, suggesting that habitable conditions could exist in places we've previously not considered. The role of Europa and Enceladus as models. To better understand the potential habitability of these far-off exoplanets, NASA turned to familiar examples closer to home: Europa and Enceladus. These moons in our solar system, orbiting Jupiter and Saturn respectively, serve as real-life models that illuminate what might be happening on distant worlds. Europa and Enceladus are fascinating because despite being icy and cold on the surface, they are believed to have subsurface oceans kept liquid by internal heating mechanisms. Europa's ocean, for example, is heated by tidal forces from Jupiter's immense gravity. Similarly, Enceladus shows signs of geothermal activity, as evidenced by the plumes of water vapor and ice particles that its orbiting spacecraft have detected. NASA's studies on these 17 exoplanets involve applying what we've learned from Europa and Enceladus. By understanding how tidal forces and radioactive decay allow these moons to maintain liquid water beneath their icy exteriors, scientists can make educated estimates about the conditions on exoplanets far beyond our solar system. This approach helps bridge the vast distances of space, allowing us to make informed guesses about worlds we cannot yet visit. It's a clear example of how exploring our own solar system can provide crucial insights into the mysteries of the wider universe. Variation in ice shell thickness and geyser activity. Exploring the exoplanets NASA identified, one striking feature is the variation in the thickness of their ice shells. This thickness isn't just a minor detail, it plays a crucial role in the likelihood and intensity of geyser activity on these planets. Just like ice on a winter pond, the thicker the ice, the harder it is for anything to break through. On some of these exoplanets, the ice could be relatively thin, similar to the icy crusts of Europa and Enceladus in our own solar system. This thinner ice could potentially allow for more frequent and intense geysers, as the internal heat has a shorter distance to travel to break through the surface. Conversely, planets with thicker ice layers might experience less frequent or less intense geyser activity, as the heat from the interior would have to work much harder to reach the surface. This variability in ice thickness and the resulting geyser activity adds another layer of complexity to our understanding of these distant worlds. It's not just a matter of finding water, it's about understanding the dynamics of these unique environments. How often do these geysers erupt? How powerful are they? These are questions that can give us deeper insights into the geological and possibly biological processes occurring on these icy exoplanets. The diversity in ice thickness and geyser activity across these 17 worlds highlights the incredible variety and complexity of planetary bodies in our galaxy. Proxima Centauri b and LHS 1140b, potential for high geyser activity. Among the 17 exoplanets identified by NASA, 2 stand out due to their potential for high rates of geyser activity: Proxima Centauri b and LHS 1140b. Proxima Centauri b orbits the closest star to our solar system, Proxima Centauri, which is about 4.2 light-years away. Its position within its star's habitable zone and the likelihood of it having a rocky composition similar to Earth makes it a compelling subject for study. Given its proximity to its star, the tidal forces exerted could be strong enough to produce significant geothermal activity, potentially leading to intense geyser eruptions. LHS 1140b, on the other hand, orbits a red dwarf star about 40 light-years away in the constellation of Cetus. It's known for its size and mass, which are both larger than Earth's, suggesting the presence of a substantial atmosphere and possibly an environment conducive to liquid water. The combination of these factors could result in a high level of geothermal and volcanic activity, including the possibility of spectacular geyser displays. These 2 exoplanets therefore offer fascinating possibilities. If their conditions are indeed conducive to geyser activity, they could provide invaluable insights into the geophysical dynamics of planets beyond our solar system and further our understanding of potential habitable environments in the universe. Observational techniques, detecting water vapor and cryovolcanic activity. The methods used to detect water vapor and cryovolcanic activity on these distant exoplanets are both innovative and complex. One key technique involves observing exoplanets as they transit, or pass in front of, their host stars. During a transit, scientists can analyze the starlight that filters through the planet's atmosphere. This analysis can reveal the presence of water vapor and other chemicals, providing clues about the planet's composition and potential geological activity. Additionally, cryovolcanic activity, such as geyser eruptions, can be inferred from changes in the light reflected by the planet. If a planet like Proxima Centauri b or LHS 1140b exhibits increased brightness or changes in its light spectrum, it could indicate active geysers spewing materials into space. These observations require highly sensitive instruments, and advancements in telescope technology are making these detections more feasible. Implications for the search for extraterrestrial life. The discoveries surrounding these exoplanets have significant implications for the ongoing search for extraterrestrial life. As we learn more about the varied conditions under which planets can maintain liquid water, our concept of habitability expands. The realization that life could exist in environments vastly different from Earth's changes the game in our cosmic search. For decades, the search for extraterrestrial life focused primarily on Earth-like planets within habitable zones of their stars. However, the recent findings suggest that life could thrive under a range of conditions, such as beneath the ice shells of distant, cold planets. This opens up a broader section of the galaxy for exploration and study, increasing the chances of finding extraterrestrial life. Moreover, these discoveries highlight the importance of advancing our observational technologies. As we develop more sensitive instruments and techniques, we may soon be able to detect signs of life on these and other distant worlds.